Let's do some further maths here. We are going to talk all things de Moivre. Abraham de Moivre, 18th century, early 18th century, with all his discoveries, or his main ones, about complex numbers and trigonometry. Let's see what he says. Now, first of all, what is de Moivre's theorem? Well, actually, originally, it's the first form of de Moivre that came out was, let's see if I can remember this. See if I can remember this in one go. Cos n theta plus I sine n theta to the 1 over n plus 1/2 cos n theta minus I sine theta to the 1 over n. I kid you not, this is the actual first draft of de Moivre's theorem. This is what he presented to people about 15 years before the more famous version that we tend to use. But obviously this is where I would start, this is where I'd get to, and he proved this for all the integers. Now we know that we can do something similar, but we will actually see later where we can get this. Right. Now first of all, we're going to start de Moivre with just z is cos theta plus I sine theta, and we now have a nice way of writing that is e to the I theta. We therefore can say that z to the n, which is cos theta plus I sine theta to the n, well, that is equal to I to the n theta, which is the same thing as cos n theta plus I sine n theta. So really what it boils down to is this is the fact that cos theta plus I sine n plus I sine theta to the n is equal to cos n theta plus I sine n theta. And that is the crux of the issue, this chappy here. I might jump around from notation to notation, but let's keep going on this little tour. Let's make a little bit of room, and we will start with our first way to use de Moivre, which is taking powers of complex numbers. On a very, very simple basis, what if I want to do 1 plus I to the power of 8? I could choose any of them, but this one makes me happy. All right, shush. Now, the idea is this. We're going to write this in terms of cos theta and sine theta, and we can do that. We can write that that is root 2 cos pi over 4 plus I. By pi over 4, I mean pi over 4. Say pi over 4, write pi over 8. Good braining. All of that to the power of 8. And this is where de Moivre come in. I could do a giant long binomial on that one, but I don't want to because that's just not how I roll. Root 2 to the power of 8, and then I can use de Moivre on this one. That becomes cos of 8 times pi over 4 plus I sine of 8 times pi over 4. So that becomes root 2 to the power of 8, that's 2 to the power of 4, that's 16. And then we end up with cos of 2 pi plus sine of 2 pi. So that just becomes times 1. So is in fact 16. But we could end up with any number of things, but that is just one example. So we can take powers using de Moivre, which also means we can take roots. Let's clean the board. So if we want to solve w to the 4 is minus 8 plus 8 root 3, we can use de Moivre for that, because finding fourth roots. Now, the first thing to do, as we did in our previous one, is write this in modulus argument form, which we can do in any number of ways, but I do believe that this comes out as 16 e to the I 2 pi over 3. And I think that works out. And here is the trick. Of course, 2 pi over 3 is not the only one, and this is where this is going to come in for us, but I'll show you in a second. And we're going to say that that is r to the 4 e to the I 4 theta. And really, de Moivre does come down to exponential form. Modulus argument form makes this much, much easier for me. Because what we can do, there's two things we need to do here. One of which is we need to point out that this 2 pi over 3, we can whack on any number of 2 pi's that we want. That is very, very important. And then all we need to do is look at the moduli. So we get r to the 4 is 16 So r is 2. R needs to be real. So that's important. And then we can look at our arguments, which will tell me that 4 theta is 2 pi over 3 plus 2k pi. Divide by 4. And that might be easier if I write that in a different way. So we get 4 roots because we get theta is pi over 6. We could add 3 pi over 6, so that's 4 pi over 6. I'll just leave them as pi's over 6's. We could get 7 pi over 6, and we could get 11 pi over 6. There's a lot to talk about here in terms of Argand diagrams, but really this is where de Moivre comes in, and we will see that our roots all have a radius of 2. And we've got one here at pi over 6, one at 4 pi over 6, which is about there, one at 7 pi over 6, which is there, plus 3. Yeah. So we're going up in pi over 2's, in fact. So what am I doing? Boop. 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 Obviously, I am eyeballing it, and they are equally spaced out around that circle. Okay, so we can take we can take powers using de Moivre, we can take roots. What else can we do? Let's do some trig identities. There are 2 main forms of trig identities that we're going to use de Moivre. You either start with a power of cos and sine, or we have something linear. And the idea is this: depending on what we want to do, we might want to start with powers and end up with nice linears. So cos 2 theta, cos 3 theta, cos 5 theta, sine 7 theta. Or we might start with something linear, cos 6 theta, cos 13 theta, and we want to end up with powers. How we approach these are quite different. We're going to start with this one here. We're going to start with this one here. How do we go from cos something theta, sine something theta to powers? Well, we just straight up use de Moivre in its barest form, which is the fact that cos n theta plus I sine theta and we're just going to use the binomial distribution, expansion. All right, let's do one that is nice and basic to explain that. So for example, we could see that cos 3 theta plus I sine 3 theta is cos theta plus I sine theta cubed. For the purpose of this video, we're going to keep a nice small power. You can do it with quite big ones. It gets a bit like, okay? And let's expand this right-hand side. We get a cos cubed. We get a 3i cos squared theta sine theta. We get a minus 3 cos theta sine squared theta. And we get a minus 3 sine cubed. And what we do is we compare real and imaginaries. We compare the real parts because 2 complex numbers are equal if their real parts are equal and their imaginary parts are equal. And we end up in its purest form with these 2 identities. Now, what we can do after that, completely up to you, completely up to the question. Maybe I only want cos thetas. Well, that's okay, because I know that I could always write that sine squared is 1 minus cos squared theta. I could do that. Same here, I could write cos squared is 1 minus sine squared and change it up that way. What else could I do? I could find tan 3 theta at this point. We have so many options of what we can do from here. But in terms of our use of de Moivre, here it is, and here is where we go. So this is our key when we want to go from something nice and linear into powers of singular cos theta, sine theta. It has a lot of uses. What about the other one? Let's check that. Right, before we go any further here, we're going to establish something very quickly. Now, if I say that Z is just cos theta plus I sine theta, which is e to the I theta, something to realize is that Z to the minus 1, by virtue of, to be fair, by virtue of de Moivre, tells me that Z to the minus 1 is cos of minus theta plus I sine of minus theta. But cos minus theta is cos theta, and sine of minus theta is minus sine theta, which is also e to the minus I theta. How that is helpful to me is that I can get these two identities by looking at these ones. Cool that. So we can see that cos theta is z plus z minus 1 over 2. And we can see that sine theta is z minus z minus 1 over 2. This is where that very first identity, that very first one that Mr. Abraham de Moivre presented to the world, that is where that comes from. All right? Take a second, we'll come back to that right at the end. But here is where we go. So, why is that helpful for me? Commit these to memory, because we're going to use them. Let's say I want to start with cos cubed theta. We are going to write this the other way around and use the binomial expansion. So you'll notice that these trig identities, we're going to use the binomial expansion a lot. So instead of starting with the other form of de Moivre's theorem, I'm going to write cos theta as z plus z to the minus 1 over 2, all cubed. And there we go. Then we expand. After that, there is one more step. This is possibly trickier than the other one. So I'm going to take out the 1/2. And what do I have left? I end up with a z cubed, a 3z, a 3z to the minus 1, and a z to the minus 3. What you will notice is you will always, always, always be able to group the positive and negative powers. When you do this expansion, no matter what that power is, you might have started with a sign, it doesn't matter, you will be able to group those powers. So I end up with 1 over 2 cubed, and I end up with z cubed plus z to the minus 3, plus 3 times z plus z to the minus 1. Now what I am going to do is I'm going to steal one of the 2's from here. This is why I kept it as 2 cubed, to get z cubed plus z to the minus 3 over 2, plus 3 times z Now, what does that tell me? This here, remember that we could also get a version of this where cos n theta is z to the n plus z to the minus n over 2. And we can get another version of this of sine n theta is z to the n minus z to the minus n over 2i. So what this is that is 1/4 cos 3 theta plus 3 cos theta. And that is the game we play in this sort of situation. We're going to use this fact, and we crack on from there. Okay, powers, roots. We can go from linear causes to powers. We can go from powers of, I've done cos in both cases, works equally well with sine. What is our last one? Let's talk series. Voila, by magic, we've got some series on the board. Now, we've got an infinite series here for c, cos theta plus a half cos 2 theta plus 1/8 cos 4 theta, etc. And for s, can we get expressions for at least one of them? Let's do that. Now, how do we do? Basically, these always boil down to the same idea, which is we're going to write c plus is. So we're going to do c plus is. Now, what we're going to notice is we get cos theta plus I sine theta. I'm going to write that as e to the I theta. I hope nobody minds. Half cos 2 theta plus a half I sine 2 theta. That will be plus 1/2 e to the I 2 theta. This will become 1/4 e to the I 3 theta plus 1/8 e to the I 4 theta. So what you've quickly got a sense of here is the Moivre's theorem in its very trig basic idea we don't tend to use as much, because really it boils down to the exponential form, makes it quite clear for us, a very powerful meshing of ideas. And what do we have here? This is an infinite geometric sequence, series even. First term, e to the I theta, r is 1/2 e to the I theta. So my sum to infinity is a over 1 minus r. Now, it can be worth checking out a few things, but what we really need to do here is we would ideally, so c plus is, there's a geometric series in there, then we need to get rid of the complex numbers in the denominator. So I'm going to multiply the top and the bottom by 1 minus 1/2 e to the minus I theta. Little trick that people do tend to get wrong. If I want the complex conjugate of this number, I don't need to change that sign. I just need to change that e to the I theta. So we end up with e to the I theta minus 1/2 in the numerator. I end up with a 1 minus 1/2 e to the I theta. We get another minus 1/2 there, and I get plus 1/4. So we put this together, which is e to the I theta minus 1/2 over 5/4. And again, we'll see we've got these same ideas time and time and again. That's a z minus 1. So that's a 5/4 plus cos theta. Now what this is that is cos theta minus 1/2 and depending on how hung up you are on fractions, we could always multiply top and bottom by 4. Might be a little bit prettier, but the point is now that is equal to this. So the real part, cos theta minus 1/2 over that denominator, is c, and the imaginary part is my s. And there we go. Beautiful, is it not? So what is all of that to do with the Moivre? Let's put all that on the board and get back to you. Right. In its most basic form, cos theta I sine n theta, which is very, very helpful. If I have w to the n is equal to, I don't know, r e to the I theta, we want to solve something in any form like this one. Remember, we're going to put a little plus 2k pi up there. We're going to write that as r to the n e to the I n, I don't know, let's actually call that one alpha. And as we do time and time and time again, that is equal to that. This is equal to this. Powers and roots. Let's go. We can also just expand that one straight up. So take our basic form of de Moivre and expand the right-hand side. Whatever the value of n in, compare real sides, imaginary sides. Bosh, you've got yourself an identity. If we write z is e to the I theta is cos theta plus I sine n theta, then z to the n is cos theta plus I sine n theta. And we can quickly see that cos n theta is z to the n plus z to the minus n over 2. But it's also equal to we can expand that to get an identity for cos n theta. We can expand that to get an identity if we group terms in this form. This by far the most tedious square to do. We've got a couple of infinite series, or they don't even have to be infinite, but those are a real pain. We get c plus is equals a geometric series, so it's equal to a over 1 minus r, and then we just have to play with that. Those are the main 4 use cases of de Moivre that I can think of that we get to use again and again and again when we're playing with further maths. Can you think of any others? Was this helpful? Let me know in the comments below. Like the video, don't forget to subscribe to the channel and hit the notification so you get more little instructional videos like this coming your way. From me here, Nick, at my Headspace. See you soon.